The Shimano Nexus and Alfine 8-speed gear hubs have become a popular choice among recreational, commuter, and utility cyclists. Beyond the clean look and simple chain line, they offer several benefits over comparable derailleur systems. A single shifter with sequentially numbered gears, no overlap to worry about as with dual derailleur systems. The ability to shift while stopped, and the simple set-it-and-forget-it shifting system make it very appealing for many riders. Most riders are content to remain blissfully ignorant about the mechanical workings inside the hub. But for those with inquiring minds that wonder, just how does this thing work? I now offer this video, the Shimano Nexus Alfine 8-speed, how it works. Like all internally geared bicycle hubs, the Shimano Alfine Nexus works on the planetary or epicyclic gearing principle. The basic planetary gear train consists of a sun gear, planetary gears which revolve about the sun gear and are mounted in a cage or a carrier, and the ring gear, which has gear teeth on its inner circumference and meshes with the planetary gears. In order to function, one of these units must be the input, or the means by which the power is delivered into the assembly, an output, which is the component which transmits the final drive ratio to the wheel, and one of the components must be fixed, or reactionary. That means it's held in place so that the other components can react against it. For bicycle gear hub applications, the sun gear is always the reactionary gear. Now let's take a look at how the direction of power flow through the hub affects the relationship of ratios between input and output. When the ring gear is the input, and the planetary carrier is the output, and the sun gear is the fixed reactionary gear, the result is underdrive. When the planetary carrier is the input, and the ring gear is the output, and the sun gear is the fixed reactionary, the result is overdrive. The ratio differential is governed by the difference in size between the sun gear and the ring gear. The greater the size of the sun gear in relationship to the ring gear, the greater the differential in speed between the two. This is an important point to remember. We will be bringing it up later as we explore the hub. So now we will take a look at how these principles are applied to achieve 8 distinct drive ratios in a Nexus Alfine hub. The design is essentially a 4-speed hub with a high and low range. There is no overlap or redundant gears, so the dual range doubles the 4 speeds to 8. First, a word about how the power is delivered into the internal mechanism and from there to the hub shell to power the bicycle forward. The power input is by means of the cog, which is driven by the chain from the pedals. The cog is mounted on the driver, which transmits the power into the internal mechanism by means of a roller clutch to transmit the power to a ring gear to achieve low range, or a positive clutch which bypasses the low range reduction and engages directly to the planetary carrier for a direct drive ratio. The transition between low range underdrive and direct drive occurs when shifting from 4th to 5th gear. The power is transmitted from the internal mechanism to the hub shell by one of 2 additional roller clutches. Which of these clutches transmits the power depends on whether any of the sun gears in the ring gear carrier are coupled to the axle by means of the rising pawls or not. The roller clutches consist of smooth steel rollers caged in a metal ring. When power is transmitted to the clutch in a forward rotation, the rollers ride up ramps and are pressed against a steel track with a force great enough to create friction between the rollers and the steel track. In this way, power is smoothly applied, and force is transmitted from one component to the other. When no forward rotational power is delivered, or if the driven component tries to freewheel over the roller clutch, the rollers are drawn back by a spring which returns the ring to its default neutral position. This allows for backpedaling or coasting. Now we move on to studying the power flow in each gear. First we will look at the low range reduction unit, which is the first stage of the power flow. When the gear selector is in any of the first 4 gears, the driver transmits power to the low range ring gear. The ring gear drives a set of planetary gears which is mounted in the gear carrier. The planetaries rotate about the low range sun gear, which is permanently affixed to the axle. Therefore the input is the ring gear and the output is the planetaries. If you remember the power flow discussion in the introduction, this means that the output ratio is underdrive. Specifically, a ratio of 1 revolution input to 0.527 revolutions output. This ratio is constant throughout gears 1 through 4. Within the gear carrier are 3 sun gears of varying size and matching stepped planetary gear sets. These planetaries drive a ring gear on which is mounted a roller clutch, which transmits power to the hub shell. Going back to the introduction, the larger the sun gear in relation to the ring gear, the greater the differential in speed between the units. The sun gears are engaged by means of rising pawls, which are actuated by the shifter through an actuation arm. In order for power to be transmitted to the ring gear, one of the sun gears must be coupled to the axle to become the fixed reactionary gear. Sun gears not coupled to the axle are free to rotate and will not function as a reactionary element. When the shifter is in the first gear position, all 3 pawls are retracted and none of the sun gears are engaged. This means that no power is transmitted to the ring gear, so the ring gear roller clutch does not drive the hub shell. In this instance, the roller clutch mounted on the end of the gear carrier transmits the power to the hub shell at the 1 to 0.527 ratio. When the shifter is moved to second gear position, the outer pawl is actuated and couples the smallest of the 3 sun gears to the axle. Now we have a reactionary gear, so power is transmitted to the ring gear at an increased speed, and the roller clutch drives the hub shell. The ratio between the gear carrier and the ring gear is 1 input revolution to 1.223 output revolutions. But because of the low range reduction at the input end, the compounded ratio is 1 input revolution to 0.644 output revolutions. Because the ring gear roller clutch is driving the hub shell at a speed greater than the speed of the gear carrier, the roller clutch mounted on the carrier is being overrun by the hub shell. The rollers retract and are neutralized. When the shifter is moved to the third gear position, the outer pawl retracts and the center pawl rises, coupling the middle gear to the axle. It now becomes the reactionary gear. As I pointed out earlier, the greater the size of the sun gear in relation to the ring gear, the greater the speed differential will be between the driving and the driven unit. The ring gear now rotates 1.419 revolutions, and when compounded with the low range reduction results in an input ratio of 1 input revolution to 0.748 output revolutions. When the shifter is moved to the fourth gear position, the middle pawl retracts and the inner pawl rises. Now the largest of the 3 sun gears is coupled to the axle, and the drive ratio between the gear carrier and the ring gear is 1 revolution input to 1.615 revolutions output. The compounded ratio from the driver to the final output is 1 revolution to 0.851 revolutions. When the shifter is moved to the 5th gear position, the pawls are all retracted and the clutch engages the driver directly to the planetary carrier, bypassing the low range reduction gear. Here is a clip showing in greater detail how the clutch is actuated. So at this stage, I can explain the functioning of the high-low range selector. This is the clutch, which engages the driver to the gear carrier
in high range and bypasses the low range reduction unit. Now it consists of a ring with radial splines on the matching surface that engages the planet carrier, and there's a ring that actually is free floating within the clutch ring, and it has two tabs on it. Those tabs ride in these slots on this cup, and when you install it you have to be very careful to make sure that those tabs are engaged with those slots. So the way that it works is, I'll turn this so that the camera can see it. These tabs ride along this surface here as the shifter is rotated. So gears 1 through 4, as it rotates, these tabs move along this surface here. When the shifter moves to gear number 5, those tabs ride down that sloped ramp, and gears 5 through 8, the tabs ride along this lower ridge. So the spring actually pushes on the clutch, and when it rides down that ramp, it engages with the planet carrier and gives you your high range. So I can give you a little demonstration of that by putting the clutch in the slots, alright, and then rotating this, and when it gets to the position where fifth gear would happen, you'll see it drop down. Okay, so low range, the clutch is up; high range, the clutch is down. Low range, high range, and that's that.
In fifth gear, with the driver coupled directly to the planetary carrier and all three pawls retracted, once again there is no power flow to the output ring gear. This means that the roller clutch on the planetary carrier drives the hub shell directly. This results in 1 revolution input to 1 revolution output, or direct drive. 6th, 7th, and 8th gear are a repeat of 2nd, 3rd, and 4th, without the low range reduction. 6th gear is a ratio of 1 input revolution to 1.223 revolutions output. 7th gear is 1 revolution input to 1.419 output revolutions. And 8th gear yields 1.615 output revolutions to 1 input revolution. This concludes this episode. I hope I have helped to demystify this unit for all of you. Here are some links to some of my other videos in the GearHubs Demystified series. I hope you will watch and enjoy them all. Please post your comments below. Thank you for watching.